Hello and welcome back to Functional Analysis. And as always, I want to thank all the nice people that make this video possible by supporting me on Steady or PayPal. Now we have reached part 16 in our course and we'll talk about compactness today. The word compact you find very often in functional analysis, however here we first go back to metric spaces. It's a property we define for subsets in a metric space and it should extend the finiteness. So a finite set should always be compact. Then for an infinite set, the compactness would say that your movement is still restricted in a similar way. To get an idea what this actually means, let's look at a subset in Rn. Of course we have Rn with our usual Euclidean metric. Now you know what it means to say that A is a closed set. The whole boundary should belong to the whole set itself, which means you can't leave it from the inside by using a sequence. So you see, this is one restriction you have for your movement. And another one comes in if you look at a bounded set. This simply means that there is a maximal distance you can go. You are not allowed to go to infinity. Now you might already know, these two things together is what we can shorten to compact. However, please be careful, actually this is not a definition. This is a fact we only have in Rn, or if you want, also in Cn together with the standard metric. Therefore the correct question here would be, how can we define compact in general such that we get the correct notion for infinite sets? Of course, this is now what we will do. So let's fix a metric space Xd. In the same way as before, let's consider a subset of this space. And now we define this as a compact set, or more concretely, as a sequentially compact set. Maybe you already recognize the same thing that happened in the continuity definition. There are two terms you could define, one with sequences and the other one without sequences. And then the result for metric spaces is they are equivalent. It's the same thing here, but I don't want to bother you with the actual compact definition. The term sequentially compact is just easier to understand and we just call it compact now. However, please keep in mind, when you're not working in metric spaces but in general topological spaces, you have two terms that are not equivalent. For us it's not a problem here, we call A compact if for each sequence in A, we find a convergent subsequence where the limit x tilde still lies in the set A. So you see there's a lot going on here. You start with a sequence, then you omit some members, which means that you get a subsequence which is also convergent where the limit still lies in A. In the picture this would mean inside the set A we have infinitely many points given by the sequence xn. Of course a lot can happen for this sequence, but compact now means that you can choose infinitely many points in the sequence such that you get a limit out. For example, here only one part remains where we have convergence to a point x tilde. And this should work no matter which sequence you started with. Now if you go back to Rn with this knowledge, you immediately see this excludes unboundedness. Because if you tend to infinity, you can't find such a convergent subsequence. Also the set has to be closed, otherwise you can just choose a sequence that has a limit outside of the set A. Then of course you can't add a new limit with a subsequence. Okay, next let's look at some examples. For the first example let's choose a more concrete one than the one from above. So this should be just the real number line together with the standard metric, the Euclidean metric, which is given by the absolute value. And the set A should be given as the unit interval. Now in this one-dimensional case, you should see that the formulation with the sequences and the convergent subsequence is exactly what you learn in analysis. It's the famous Bolzano-Weierstrass theorem. Then with this in the toolset, one can easily show the equality here for Rn or Cn with the standard metric. Therefore, let's now look at the same sets together with another metric. So again, the real number line, but now with the discrete metric. Now you might already guess, in this case, the unit interval is not compact. In order to show this, you just have to find one sequence which has no convergent subsequence at all. Hence, let's simply do that. Okay, so let's choose the sequence xn by setting xn as 1 over n. It's a sequence inside the unit interval, but it's not constant. Hence, we already know what the distance is between two members of the sequence. We are in the discrete metric space, so we get always 1 for two different points. However, this now means that we could omit a lot of members in the sequence, but we never get the 1 down to 0 here. In other words, there can't be any convergent subsequence. In conclusion, the unit interval is not compact with respect to the discrete metric. Okay, so please keep that in mind. Always emphasize the corresponding metric when talking about compact sets. Now for the end of the video, I want to show you a nice proposition which generalizes the result from above. We have our metric space XD and a compact set A. Then we can conclude, so it's an implication, not an equivalence, that A is closed and bounded. So in general, we still have the result that closedness and boundedness is needed for the compactness. It's not the other way around. Compactness in general is more, but this can still be helpful. Before writing down the proof, we should first define what we mean by a bounded set inside a metric space. Of course, this is not so surprising if you have your set A here. It simply means that you can find a large enough epsilon ball such that the whole set lies inside this ball. So we just have to find a middle point x and a radius epsilon. And then we want that the open epsilon ball around x is a superset for A. And this is what we mean when we say bounded. It simply means that there is a constant such that any 2 points have distance less than this constant. And here you see this constant would be just 2 epsilon. Okay, by knowing all the terms in the proposition, we now can write down the proof. Starting from a compact set, we have to do two things. First, we want to show that A is closed, so let's choose a convergent sequence in A. Hence we know there is a limit x tilde in X. Now recall, if we can show that x tilde is actually in A, then A is closed. Using the compactness, we immediately get the result for a subsequence. Hence we have a convergent subsequence with limit in A, and maybe we call this limit x tilde tilde. Of course, this is not necessary because we know we already started with a convergent sequence. And we know the limit is always unique. You can't find another limit with a subsequence. Hence x tilde and x tilde tilde do coincide, so we know x tilde lies also in A. This is exactly what we wanted to show, therefore A is closed. Okay, then the next step is showing that A is bounded. We do this with a proof by contraposition. This means that we start with A being not bounded and we want to end with A being not compact. Now, if A is not bounded, we know that we can find distances as large as we want. Hence, for a given point A in the set A, we find infinitely many points xn in A such that the distance to A is larger than the natural number n. With this, we have one sequence xn in A where we can look at all possible subsequences. Now, if A was compact, we would find a subsequence with a limit. Therefore, let's look at all possible limit points as well. Hence, we would be interested in the distance between the limit point B and the sequence xnk. Simply because if the sequence was convergent, this would go to 0. However, the only distance we know at this point is the distance between A and xn. And using the subsequence, we know this is larger than nk. Then on the right hand side, we simply can use our triangle inequality. We just put B in the middle. Then bring the one part on the other side and we get the following inequality. So we conclude the distance between any point B and a sequence member x and k is always larger or equal than this part here. However, seeing the nk here, you know you can make the left hand side as large as you want. Hence our conclusion is, no matter which point B you choose, if you send k to infinity, this will never go to 0. So there can't be any limit point for the subsequence. if you fix a point B here, you will always run away from it. And therefore, A is not compact, because we found a sequence which does not own any convergent subsequence. And by contraposition, we finished our proof. A compact set is always bounded. Okay, so now you know the notion compact for metric spaces, and in the next videos we will extend this to operators. So I hope I see you there. Thanks for listening and bye!